All righty. Hey there. Hey there. Good evening, everybody, and welcome to part three of Takeo After Dark, the fall edition. And welcome. Glad you're here. Joining us tonight, we have Dave Holdorf. Say hi, Dave.
Howdy, y'all.
And
Good to
Rick
see you all,
Mayo.
so to speak.
Hello to
Hello,
all.
Rick Mayo. And I'm John Barba. Darn glad to meet you. And on the also on the line, we have our friends from Mechanical Hub, John Messenbrink and Tim Ward. Say hi, guys.
Hey,
Everyone, how you doing?
All right, good evening, good evening. And as you may tell, the theme tonight is another one of our favorite programs, WKRP in Cincinnati. Although Dave went off the reservation and he went to Polk High with Married with Children, but hey, that's Dave. What can
That
we
was the
say?
next channel from channel 4 to channel 5, yeah.
There you go. There you go. So welcome. Again, and tonight, tonight's part three, and we're going to be talking about pipe sizing, air control, and this whole thing about pumping away and how cool that is and how cool that is. So let's get started and again meet the gang as it were. So again, in our characterization of our crew, WKRP, my favorite program, of course, is the theme, and there's your trio. I'm going to take the role of Dr. Johnny Fever because I have the microphone, fella babies. Couldn't really, we had a tough time parceling out the other two, but Rick being the snappy dresser, of course, he's not wearing the tie-dye tonight like he was last week. But we still, because he's the snappiest dresser of the bunch, we gave him the Herb Tarlick role. And of course, Dave could be no one else but Les Nessman. Right, so tonight we're going to have more hydronics and less Nessman. There we go. Yeah, thank you. So there we go. So that's the show tonight. If this is your first time, I'm sorry if we just frightened you. Okay, but new to webinars, I just want to make sure everybody's on the same page. Look in your control panel. This is important. Check your control panel. That little orange arrow, if it's pointing to the left, click on it, and that will expand the control panel. All right, so that'll expand the control panel, and that's going to be how y'all communicate with us.
yeah.
So once you have the expanded control panel, of course, you've got your audio section up top, okay? So you get the audio section up top so you can make sure you can hear us, etc. If you just see this and you're not hearing us, my giving you instructions will be useless, but hopefully you'll see what to do. So make sure you obviously can hear and see us. Any handouts, there's a handout section there that you can download as well. So the stuff that you can have use for. And then the important part is the questions. So again, I want to make sure everybody knows how to use that. Can you type in a hey there, hi there, ho there, how are you, whatever you got, just let us know that you guys can hear us. And there we go. All right, everybody's chiming in. Hot dog.
Yeah.
Mr. Trotta, as God is my witness, I thought circulators could fly.
There you go. That's right. One of the great sitcom moments in television history.
I love that scene. I love that one. Yep.
There you go. Yeah. And again, type in your questions right in there. So it seems everybody's got that idea. So good. And as we go along, again, just type in your questions as we go along. We'll stop and check every few minutes, every few slides to see how we're doing, do a status check, make sure you're still with us, make sure we haven't lost our internet connection or anything silly like that. And answer questions as we go along. We're not going to wait till the end to answer your questions. We'll answer them as we go. And then like we do every week, we'll stay on as long as you guys want to talk. So, and that's one of the things that makes Takeo After Dark so much fun, the after hours sessions. So I think it's time for us to get this show on the road. What do you guys think?
Let's go.
All right, let's go. Let's
Rock and roll.
It's time for this town to get down. All right, where did we leave off last week, boys? I think we left off here. Remember, we talked about the basics of fin tube baseboard. We talked about average water temperature versus supply water temperature, 4 gallon a minute versus 1 gallon a minute output charts, and make sure you use the right column and the right row for your specific application. And we also talked about ratings for baseboard at lower water temperatures. You don't have to run 180 degree supply, 170 average. You can run it down as low as the baseboard itself is rated for. Here, Sterling Petite was rated down to an average of 150. We saw last week that slant fin was rated down to an average of 110, which is kind of crazy. We also talked extensively about cast iron radiators, columns, tubes, height, sections, equivalent direct radiation, and how to figure that out, and how to figure the output at lower water temperatures as well. So we went through all of that last week, as well as touching upon radiant floor heating, some fundamentals of radiant floor heating, as well as boiler selection and the difference between AFUE rating, the difference between the DOE output and the net IBR or net AHRI output. So we talked about both of those last week. So for this week, we're going to get started with getting into some of the meat and potatoes of actually delivering BTUs, all right? So what we're going to start with here is something called the universal hydronics formula. We go through this in every class we do because as we said earlier in episode 1, that there's math to hydronics, right? There's math here. It is a science. It's not an art form. It's a science, and it's based in arithmetic. The math itself isn't very hard. It's addition, subtraction, multiplication, and division that we all know how to do. It's just how to apply it is the challenging part. But this math formula, of all of the different formulas out there, all the different math things out there that we have that are involved, in my mind, and Dave and Rick, you chime in if you think if this makes sense. This is the this is the one you got to know by heart. This is the one you got to have memorized, and you can not only recite it, but apply it and use it as comfortably and as confidently as you tell people your name and address. You guys are in agreement with that?
Yeah, I agree.
Oh, and if you don't have that piece of paper around any longer, then you should tattoo it right on your forearm so you can look down at it every time. Yes.
Yep. Right on your knuckles.
Right on your knuckles. I know a wholesaler actually who on his business cards, on the back of his business cards, he gets them printed 2 sides, and he has all of these math formulas on his business card. So he gives you your business card. You have that stuff, and it's a reason for you to hang on to his business card, which makes it smart, but it's also very useful. And the universal hydronics formula states that GPM is equal to BTUH divided by the product of delta T times 500. GPM equals BTUH divided by delta T times 500. This is an important formula. We're going to use it to size pipe. We'll use it to help size pumps, and we'll use it to troubleshoot. Other than that, it's probably not necessary, he said sarcastically. But it's that important. GPM equals BTUH divided by delta T times 500. This formula is as important to us as anatomy is to a doctor or torts are to a lawyer. They got to know it, right? Same thing here. Got to know it and got to be able to use it. Let's identify the terms real quick. GPM, of course, is your gallons per minute flow rate. We deliver BTUs through using water, right? And when you move water, you're moving gallons per minute. In forced air, it's CFM. In hydronics, it's GPM, gallons per minute flow rates. So that's what we're trying to find out. That's what we're trying to establish. How do we establish that number? Well, we have to divide the BTU load, the BTU requirement that we're trying to deliver by the denominator of delta T times 500. Now, delta T is our designed for temperature drop across the piping circuit. And what do we normally design our hydronic systems to, ladies and gentlemen out there? Generally a delta T of 20. All right, meaning the water goes out at one temperature, it comes back 20 degrees lower, like 180 out, 160 back, average of 170. 140 out, 120 back, average of 130. There would be instances where we might design to a wider delta T. We might design to a 30-degree delta T for, let's say, a snowmelt system. Or we would design to a 30-degree delta T for to size the boiler circulator and the piping and the flow rate across the heat exchanger of a modulating condensing boiler, perhaps. We might also design certain systems, particularly radiant floor heating systems, residential radiant floor heating systems, in some cases to a delta T of 10, meaning the water goes out at 120, comes back at 110 for an average of 125. Why would we do that? Well, that's done for comfort and consistency of floor surface temperatures. So the delta T that we design for is going to be dependent upon the application. In most cases, it is in fact 20 in heating systems that are designed in North America. Now, the 500 is a mathematical shortcut, and the 500 has some variation to it, but typically we use that as a math shortcut for this formula. And what it is, you derive that by multiplying the weight of 1 gallon of water. 1 US gallon weighs 8.33 pounds, times the minutes in an hour, and then 1 US hour has 60 minutes in an hour, times the specific gravity of the fluid. Water, 100% water has a specific gravity of 1, times the specific heat of the fluid. 100% water has a specific heat of 1. So 8.33 times 60 times 1 is 499.8. And we'll call it 500. Now, Rick, under what circumstances might that number change?
Well, a lot of people probably listening occasionally mix this water with glycol, and glycol's specific heat is less, and we have a deduct for that. So that'll see that number begin to drop as the temperature goes up, as well as the glycol mixture goes up. That's the first thing that comes to my mind.
All right, and a lot of that's based on the density too of the water. Now, as water increases in temperature, its density goes down, right? So as the water gets hotter, you might see that 500 number drop. Like in your instances, you usually design using 490 instead of 500.
For hotter water, yeah, that's about 140 degrees. So again, it's slightly less than that at 180, so on and so forth.
Right. So, but this
Yeah.
will get you in the ballpark and get you into to be able to size your circulator and to size your piping. So just understand that it can change. Glycol does have a bigger effect. It can actually drop that number down as low as 465, 470, or maybe even as low as 435, 430, 435 when you go into a 50-50 glycol mix for snow melting. So
Should
just
be around
understand.
450. 450 for 50%.
450. Okay.
450. Yeah.
Very good. Very good. And the thing about glycol is they're not all the same. That's the funny thing about glycol. They're not all the same density. They're not all the same chemical formula. It depends on what you're using. If you're using some stuff that's already pre-mixed and you just, it's already diluted and you pump it right in. I've seen stuff that actually on the jug, it says use 491 or something like that. And then there's others that you mix outside of the system and then pump it in, that's going to drop that considerably lower, again, depending upon your concentration. The thing is, you got to look at the jug to see what you're doing. So for 100% water, the formula is written here will do you just fine. All right.
Since we're talking about glycol, I'd like to throw one thing in there, and it just try to get everybody to understand how to read those two columns. We have a freeze and we have a burst. Most people in the HVAC business that are in the heating business do not need to use the freeze column, use the burst column. We won't take the time to go through all that tonight, but that if that sparks your interest, make a note of it and look at your glycols and look at the two columns and make sure you're using the right column. What I'm getting at is it leads to over mixing, making mixture actually thicker than it needs to be.
Very good, very good. And we'll include a little section on glycol, I think, in subsequent classes. We have some good information on that for you. So good. So let's apply this formula real simply. GPM equals BTUH divided by delta T times 500. So let's say I'm trying to size a circulator for a single zone, and that single zone has 25,000 BTUs on it, so 25K on this single zone. So to find the flow rate, I'm going to divide 25,000, and this is, let's call it baseboard or whatever, and it's designed to a 20-degree delta T. So I'm going to divide 25,000 by 20 times 500 or 10,000, and you can divide anything by 10,000, right? So 25,000 divided by 10,000, the gallons per minute flow rate I need for that zone under design conditions on the coldest day of the year is going to be 2.5 gallons per minute. Now here's a pop quiz for you. What if it's 50% load? All right, what if it's not 100% load? What if it's 50% load? That would be 12,500 BTUs. What would the flow rate be then? All right, let's see what you guys think. What would the flow rate be at 50% load when the load was only 12,500? Type in your answer. What do you think that would be? Yep, you got it, Richard. Very good. Yep. Everybody else, let's see what you got. Type it in, people.
Here's
We got
hint.
a batch of you there.
It's linear.
It's linear. That's right. It is linear. So it'd be 12,500 divided by 10,000. So 1.25 GPM. Excellent. Very good. Very good. So again, it changes. The required flow rate will change with the heat load. Keep that one in your hip pocket. A couple sessions from now, that'll become really, really important. But the flow rate required flow rate changes with the BTU load, okay? With the BTU load. So how do we use that when we're sizing the pipe? Well, okay, we have to figure out. Let's say we're going to size our boiler pipe, okay? And this is for the sample house that we've been doing. And let's say this is a cast iron boiler, and we want to size our supply and our return pipe. We want to size that. We want to size the air separator, etc. So we got to find the flow. To find the flow, it's GPM divided by BTUH equals BTUH divided by the product of delta T times 500. Our required BTU load, remember when we did the heat loss 2 weeks ago, it came out to 82,401 BTUs. So 82,401 divided by 20 times 500 or 10,000, that's going to be 8.24, we call it 8.2, 8.3, close enough. That's the required flow rate for that BTU load, and our piping has to be sized to carry 8.2 GPM. Now, what size pipe does that need to be? Well, again, here's your pipe sizing guidelines. And these are important to keep in mind because this is just default for closed loop hydronic systems. For closed loop hydronic systems, if the flow rate's between 2 and 4 GPM, 2 to 4 GPM, we're going to talk about 3/4 inch copper. 4 to 9 GPM is 1 inch. 8 to 14 is 1.25 inches. I know there's an overlap there. We'll explain in a second. And then 14 to 22 is 1.5 inches. Why is this important to know? Well, if we do the math and we find that we only need a 1 inch header, then why in heck would we bother installing an 1.25 inch header, right? 1.25 inch pipes more expensive than 1 inch. 1.25 inch fittings are more expensive than 1 inch. 1.25 inch air separator is more expensive than a 1 inch. I mean, go on and on and on. You want things to be priced right, well, size them right. Okay, that's where you sharpen the old pencil, so to speak.
Yeah, a lot of people will say, yeah, exactly, sharpening the pencil. No, we're not, or you're not value engineering it here. Well,
Right.
guess what you're doing? You're engineering it.
Exactly. Big difference.
There's a big difference between value engineering and this. Yes.
Yeah. So in this case, 8.2 GPM, we're looking at 1 inch copper pipe for our header. 1 inch coming out of the boiler, 1 inch returning back to the boiler. Now, why do we have that overlap between 1 inch and 1.25 inches? Well, it has to do with why these guidelines are in fact the guidelines. All of these guidelines are based on a minimum and maximum fluid velocity. All right. GPM and velocity are kind of different. GPM is gallons per minute. Velocity, we refer to velocity in terms of feet per second. Think of GPM as capacity and think of feet per second or velocity as speed. All right, how fast is that water moving? GPM is the volume of water. Feet per second is the speed of the water. And in a closed loop hydronic system, we design to a minimum velocity of 2 feet per second and a maximum velocity of right around 4 feet per second. All right, right around 4 feet per second. Now, I can run 22 gallons a minute through 3/4 inch pipe, can't I? Hell, you give me a pump big enough, I'll make it go. We can sure as heck do that, but we'd be well in excess of 4 feet per second. All right. The guidelines are the guidelines for different reasons, on different ends. The reason we have a 4 foot per second limit on the high end is if we were pumping water at 12 feet per second, two things would happen. The first, you'd hear it. It'd make a hell of a racket. All right. Velocity noises can be anything from a to, in some cases, I've heard it actually sound like a freaking freight train going through the house. All right. It can be that bad. That's the most audible and noticeable thing. But if you're slightly above velocity guidelines, what can happen over time, and where do we see this most? We see this actually in domestic hot water recirculation lines that have been where the pump has been oversized. Is water's the universal solvent, right? It'll start wearing out pinhole leaks in the piping. So you might see at fittings first and things over time, you might see totally unexplained pinhole leak somewhere in the house, and it has to do with internal erosion caused by excessive velocity. So that's why we have the 4 foot per second max. The minimum on 2 feet per second. I mean, I could run 2 gallons a minute through 1.5 inch pipe and not break a sweat, but my velocity would be well below 2 feet per second. And what would happen then is I'd get noise of a different kind. At velocities that low, dissolved gases in the fluid have a tendency to come out of solution and turn into bubbles. And now we get babbling brook kinds of sounds and things like that. And not only does that not sound good, it also kind of impedes heat transfer and things like that, because air doesn't transfer heat as well as water does. So that's why we have the low end guideline. Now, the reason we have this overlap right here between inch and 1.25 inches, it simply has to do with the difference between type M copper and schedule 40 black iron. If you're using both would be 1 inch, right? Both would be, if I had 1 inch of each, they'd both be 1 inch. But the black iron, the schedule 40 black iron, has a thicker wall and a smaller ID, whereas the copper has a thinner wall and a bigger ID. So I can get up to 9 gallons a minute and stay within my velocity guidelines with copper. With black iron, I'm really limited to 8, if that makes sense. So that's why the guidelines are the guidelines, but doing the math, again, allows you to engineer as opposed to value engineer, as Dave was saying. All right, we have any questions in there yet, Dave? Dave and Rick, have you seen anything?
Oh, no, doing rocking and rolling.
Cool, cool, cool. All right, all right. Well, then let us continue. All right, let us continue. We're going to talk about piping up modcon boilers in a subsequent section, but suffice it to say, modcon boilers, and Rick, you can comment on this a little bit better than I can. Modcon boilers might be the easiest thing on the planet to pipe up in terms of sizing the pipe. All you got to do is what, Rick?
Well, I'd go back to some of the classes we've done in the past and figure out what the GPM is for that delta T across that boiler's heat exchanger, and that's how I'd size it. But I think you're going for something else.
Yeah, where do you find that information? In the
Manual.
in the manual, right? Read the manual.
RTFM.
You read the manual. The manual will tell you, say if I'm piping out, piping it up like this, all right? The manual will tell you what that pipe size should be. And they'll give you the information to figure out what that pump should be. The information we just shared with you is going to help you size that pipe, the header, the distribution header. All right. But this part, you'll find the information in the manual, and they'll give you a diagram and everything. They're the easiest thing in the world to pipe up. Just do what they tell you.
But yes, also what Rick said. Do the math or read the manual. Yes.
Yep. And the manual will show you how to do the math to size that pump. There you go. Very good, very good. So what's next in this world? Well, here we're going to start talking about expansion tanks and air separators and pressure reducing valves, because that's generally going to be the first thing you encounter coming out of the boiler, or on this header, it might be the first thing you see on the header for a modcon. The pressure reducing valve, the air eliminator, and the expansion tank. Now, we offer this little guy right here. This is the our 3450 Takeo combi valve. And this is a pressure reducing valve right here and a backflow preventer in one very simple package. And it's actually one unit. It's not 2 units, unioned together. It's actually one single unit that is serviceable on both this end and that end. All right. But it's a nice little combi valve. It's got some cool things to it. Again, you've got sweat, NPT, and press connections as an option. But when you're talking about setting it up, right here, there is in fact an indicator to tell you what the pressure has been set at. It doesn't tell you what the pressure is. You use the gauge on the boiler for that. But a typical pressure reducing valve, you've either got that little nut that you have to adjust, or there's a little lever to lift to go into fast fill. And if you want to adjust the pressure, there's little set screws in there. And they don't really tell you what it's set at. You kind of have to goof around with it until you get it to where you want it to be. But at the very least, when you want to change the pressure setting here, you adjust I'm moving my hand here, but you can't see that. You adjust that little dial right there, and you can change the setting, and you can see where the setting is at. That's one cool thing about it. The other cool thing, and I'm going to ask for you, I want you guys to be absolutely honest. Whenever you've had any other kind of a pressure reducing valve, and we sell the other kind as well, where you have a lever that you put it into fast fill, or a lever that you lift to put it into fast fill, and you're going to go purge, right? You go over to the purge station, you open up the valve, and you have your hose connected to the purge station, and you blow out the air. Well, we've all done it where you open the valve and you open up the fast fill and you're bleeding out the air, and the air, all of a sudden now you have a nice steady stream of water. So you go and you close the valve on the purge station. How many times, and be honest, has this ever happened to you? Did you not get back to the pressure reducing valve in time to take it out of fast fill and pop the relief valve? All right, I want honest answers in here, folks, because that's happened to me many times back when I was working with the tools, which is why I had my tools retired. Yeah, Roger Cunningham, thank you, very good. Yeah, exactly, many times, very good. Yeah, it happens. You can't be in this business and have that not happen to you. Well, what this guy does, all right, what this guy does is this little button right here, all right, this little button right here, you press that to put it into fast fill, and it'll stay there until it senses 12 psi pushing back, and then it'll pop out of fast fill automatically. You don't have to do anything. So you press that button, open up your valve, then press that button, whatever process works for you. Purge, then you're in fast fill, you purge, you close the valve on your purge station. The minute we get up to 12 psi or whatever we're set at, that thing goes pop and we're out of fast fill, which to me is really cool. I mean, just think of, again, if you've ever had that happen to you, here's a simple solution in a nice, sweet, and serviceable package. All right. Another thing we started offering this year is boiler trim kits, because a lot of people asked for them. And I don't know if you guys find these useful or not, but it's something that we do have, where we would include the air separator, fast fill backflow preventer, and an expansion tank, plus all of the associated fittings in one package. Now you can get your basic package with the standard air scoop. You can get a middle of the road package with your standard backflow preventer and pressure reducing valve and the 4900 air separator. Or you can go Christmas, New Year's, and a ban on Chinese imports all rolled into one and get the deluxe model that has the 4900 plus the 3450 combi valve and a nice little shutoff and purge station here, or shutoff and drain station there for your expansion tank service, which is kind of a cool thing. So those are available to you. It's not assembled. You have to assemble it, but all the parts that you see there are included in the kit. So that's something we offered this year as a convenience item for you guys.
It's even got a nice picture on the box. So you can it's got a nice picture of that on the box. So you give it to any one of your workers, helpers, whatever, new guy, and say, here, make it look like this.
There you go.
And the other thing with the other two kits, outside of the premium kit that has the isolation valve for the expansion tank, the other two kits have a check valve.
Yeah.
That's going to the expansion tank. So you could still take off an expansion tank and not drain, dripping water all over the place and exploding the system out on you. So you'll just, obviously, if you've got a bad expansion tank full of water, pain in the neck, you're going to want to relieve that pressure that's in there. So you're not going to be able to do it from draining the boiler side. Just drill a hole in the side of the tank, get that water out of there so it doesn't come crashing down to your foot. But you've got that check valve built in there too.
Very good. Very good. All right. Excellent. Okie dokie. Let us continue. All righty. Here's a good question for you guys. When you buy an expansion tank, okay, it is charged to 12 psi. When you buy a pressure reducing valve, it's set to 12 psi. What's so special about 12 psi? Well, there's a reason for that. Learn, if anybody's got a plumbing license, you maybe learned this day one of plumbing school. All right, a column of water 28 inches high will have a gauge pressure at the bottom of 1 PSI. Doesn't matter how big around it is, just how tall it is. So 28 inches high, I'll have a gauge pressure at the bottom of 1 PSI. All right. Another way of saying 28 inches is 2.31 feet. 2.31 feet. Okay. So in our world, 1 PSI is equal to 2.31 feet of head pressure. In other words, if I wanted to raise a column of water 2.31 feet high, I'd need 1 PSI worth of pressure. Now, everything's set up to 12 PSI, right? So if we were to multiply 12 PSI, by 2.31 feet per PSI, I'd get a total of 27.72 feet, right? 27.72 feet. 12 PSI is the amount of pressure I need to raise a column of water 27.72 feet up in the air. That's enough fill pressure, static head pressure or static fill pressure that's needed to fill and pressurize a normal residential hydronic heating system to the uppermost floor of a normal residential structure with a little bit left over for safety. So that's kind of how that works. That's why 12 PSI. That's why we do 12 PSI. All right, so it keeps everything pressurized. Now, can you boost the pressure on your fill? Can you make the fill pressure, more if you need it to be? Well, sure you can. You can fill it at 12, 13, 15, whatever pressure you want, provided that when everything's hot, you don't exceed 27 PSI. All right, because we know the relief valve will blow at 30, but it starts to weep at about 27, 28 PSI. So when everything's hot, that's kind of what we're worried about. If you increase the pressure at the fill valve, you must also increase the pressure on the air side of the expansion tank. You have to increase, whatever you do to one, you have to do to the other to make sure the acceptance volume stays consistent. Otherwise, the tank will be undersized. And the thing is, you can't add pressure to the expansion tank when there's water on the water side. You have to take the pressure off of the water side before you add air or check the air pressure on the expansion tank. That's why in the deluxe boiler trim kit, we have that little drain valve on there that would allow you to do that. The other thing about expansion tanks that's important to remember is that membrane right in here is not airtight. It's not completely insoluble to air. The manufacturers will tell you that through the magic of oxygen diffusion, molecular oxygen can pass from the air side into the water side, and you can lose up to 1 PSI worth of air charge on the air side per year. So we tell people if you go in for your annual clean, check, and adjust or annual service, it's always a good idea to check the air pressure on the tank, but you have to take the pressure off the water side before you can do that. Right? Again, that's why this valve up here is really helpful in annual service and in case you have to change the tank. So that would be the presumption there. And one surefire clue that maybe you've lost air on the air side of the tank is, again, maybe that relief valve popped for no apparent reason. All right. So those are things that certainly can happen. All righty then. How are we doing there, folks?
If you stop and think about that for a second, I run into this all the time, and a lot of people start talking about, well, the expansion tanks just suck nowadays. They're not made the same. It's different designs, and they seem to be replacing them more and more often. It's because nobody checks that air pressure. Nobody checks it. And when you stop and think about that for a second, if it loses 1 PSI per year, let's say the first year, it lost 1 pound on the air side, but you go ahead and check it without relieving the water pressure, it's going to say 12 PSI. Why is it 12 PSI? Because it needed equilibrium. How did it get to equilibrium? The PRV put some more water into the tank. Now that bladder that was up high, when that bladder was up high, now it's stretched when the water's cold and it heats up and stretches further. Now do that 3 years in a row without checking or checking the air pressure on there. Now when the water's cold, we've got an already stretched out bladder, heats up, and that's where it starts messing around. And that's why they start to fail a heck of a lot more often. So not a lot of, yes, things have changed because now expansion tanks have air in them now compared to in the past where they used to be made with some CO2. I remember reading something a bunch of years ago from Amtrol. They would actually cut off a piece of dry ice when they assembled the tank, so they would have the set amount of pressure inside of it. But they didn't have Schrader valves that you had to add to it. So just different designs that we have now.
Very
Sorry,
good.
just a
No,
little
hey.
thing I like to talk about. Yep.
Good stuff. Good stuff. Good stuff. All right, gang, it's time for the trivia question of the night. And of course, we're talking about a WKRP in Cincinnati. And at the end of the show, at the end of the presentation, we're going to pick our winners for last week. Correct, Dave? You got that all set up?
I do.
All right, yeah, for our MASH trivia question, but tonight's trivia question has to do with WKRP in Cincinnati and specifically the good doctor, Dr. Johnny Fever. All right, Dr. Johnny Fever. Dr. Johnny Fever had a long and distinguished radio career, and he was known by many names: Johnny Sunshine, Johnny Duke, Johnny Style, Johnny Cool, Johnny Midnight. Now, before he was at WKRP, he was a disc jockey in Los Angeles, and he got fired from that gig for using a specific word on the air. What word did John Caravella, that was his real name, what word did John Caravella say on the air to get fired from his gig in LA? All right, so put your answer down in the question section. We'll keep track, and when we give you the answer later on, we'll cut it off. And everybody who got the right answer, well, you'll be entered into the drawing for next week for an amazing array of valuable prizes. So that's how that's going to work. So what word did John Caravella, Johnny Sunshine, Johnny Duke, Johnny Style, Johnny Cool, Johnny Midnight, what word did he say that got him fired from his radio gig in Los Angeles that led him to WKRP in Cincinnati? All right, happy hunting, you Googlers, you. All righty. Let's get back to work. I love that show. I got to tell you, I love that show. I love that show. And my disc jockey days were exactly like that, right? Sort of. All righty. Let's get back here and talk about air eliminators. And there was one question earlier. Is it okay to put a shutoff valve on an expansion tank? Yeah. Again, some local codes may frown on it, and you got to do what the local codes say, right? But many local codes say it's fine, especially if it's there for a specific purpose in terms of service. So yeah, and I've seen some people actually would put a ball valve there and they'll take the handle off so nobody can accidentally close it. So those are all kinds of things that you can do. But again, whatever your local code, of course, is required. Alrighty. Let's talk about air eliminators, air letter outers, okay? We have the air scoop and the 4900. And somebody asked earlier, do people still use air scoops? Oh my gosh, yeah, we sell a ton of them. There's nothing wrong with an air scoop, absolutely nothing wrong with them, provided they're installed correctly, which we'll get onto. But we do have the option of the 4900 series air separator and their brothers by Honeywell and spirovent that are air killer deaders. Basically, they kill air dead. They'll let air out of the system as fast as you can put it in it. That's an air eliminator, whereas an air scoop is more of an air control device. Okay, so we have both options. And both options have worked very well. All right, and we're going to show you how to make the scoop work as best as it can, so you have that lower priced alternative. But let's start off by saying, quite simply, air is bad. Okay, when it comes to a hydronic system, air is bad. We don't want it in there. Let's save it for blowing up footballs and basketballs and volleyballs. We don't need it in the hydronic heating system.
Sorry, I heard the football mention. Sorry.
What?
Never mind, not going there.
Okay, Giant fan. Water, let's talk about specific heat for a minute. Water has a specific heat of 1. Air has a specific heat of 0.24, which is less, okay? So air, my friends, is an insulator. You put a lot of air in the water, we're just not transferring heat quite as effectively. Water and air, put them together in a system with, say, cast iron and stuff. Well, what are those? What are those ingredients of? Ingredients of rust and crap and corrosion and things like that, which can make your system a little bit on the dirty side. And circulators aren't really good at pumping air. Circulators do a dandy job of pumping water, but they don't do a great job of pumping air, and that can reduce your flow rates and your velocities. So again, just keep the air out of the system and control it as best we can, and everything will work better for a longer period of time. All right. But here's a question. Why everything you see here, the air scoop or air eliminator is always on the supply side. Why is it always on the supply side? What do you think? Type in your thoughts here. Why is the air eliminator or air scoop always on the supply side of the boiler, of the piping system? Let's see what you think. Why is it always on the supply side? Catch it before it goes out to the system, okay? And there you go, Philip's got it. It's where the water's the hottest. It's where the water is the hottest, okay? If you've ever watched water boil, you understand. As water gets hotter, you know, in a pot, maybe making spaghetti or something, you start to see little bubbles start to appear, and then it goes, and it's boiling, right? The hotter the water, the less capable that water is of holding dissolved air in solution. Okay, it can't hold that air in solution. That water wants to turn back into a gas, all right? So if we've got an air letter outer that we can put in the system, doesn't it make sense to put the air letter outer at the point in the system where the air wants to get out the mostest, right? Why the heck are we fighting, you know, nature here? The air wants to get out. Let's let it, okay? Let's put the air separator right where the water's the hottest, so we can do the most good. So let's take a look at the scoop and the 4900. The scoop is basic, it's simple, there's no moving parts. These things are built to last, okay? They're built to last. There's a couple of rules for installing these things so they actually work, okay? The first rule is it must be installed so that you can read the writing on the side without contorting your body, okay? That means the writing, it has to be installed horizontally. So you can read Takeo air scoop, okay? You don't want it vertical, right? And you don't want it upside down. I'll tell you what, I've seen these things installed upside down where this bell thing is pointing down and the writing is upside down. The only reason I can figure is they've tightened up the, you know, the thread so much that that's where it stopped and say, oh, well, that's all we're gonna do. At that point, it's not an air eliminator, it's not an air separator. At that point, it's an expensive coupling. The other thing is, what do you think this arrow indicates? It indicates direction of flow. Now we put inlet on this side. The only reason I can think of we didn't put outlet on the other side is that it might be insulting, okay? Okay, so inlet and outlet, or gazinta and gazauta, whichever you prefer, all right? You have a little tapping for a high vent on top, and then you got a 1/2 inch tapping down below for your cold water fill with your pressure reducing valve, backflow preventer, and a connection for your expansion tank, all right? A connection for your expansion tank. So that's kind of how that thing is put together. Important thing on how it works, okay? And an important piping note that we have to take into account, all right? Now, remember we talked earlier about velocity, right? And minimum velocity. If we go below 2 feet per second, dissolved gases want to turn back and, you know, come out of solution and turn back into a bubble. Well, where do you think we'd like that to happen? We'd like that to happen in the air letter outer. How do we make that happen? We give the water a great big open space, all right? An air separator, like a scoop or even a 4900, is simply a big open space in the piping. So the water's zipping through, let's say, this 1 inch pipe, all right? And the velocity's right at 4 feet per second or really, really close. And we keep that velocity up. The dissolved gases want to come out of solution, but they can't because they're being held in solution by the velocity in the pipe. And that's very restrictive, and that's just the way it is, all right? So once it hits this big open space in the piping, the velocity slows down, man. And all of a sudden, all this weight of this velocity and everything just, the water can relax and the air can relax, the dissolved oxygen can relax. and it starts to come out of solution. It can come out and play, right? It's like you ever leave the gate open and with a dog, all right? And the dog gets out of the gate and he's free, man. He's running. He's having a great time. This is the same thing, only different without the fur, okay? Water gets into the air scoop. The velocity slows down. The dissolved gases tend to come out of solution, but it's a trap, all right? This scoop has a little turning vane inside, and it will literally scoop the bubbles into the upper portion of the chamber and let them go out the air vent. Okay, it literally just it's literally a scoop. This is the important part here, boys and girls. You must, no ifs, ands, or buts about it. You must have 18 inches. That is 1.5 feet, 18 inches of straight, uninterrupted pipe into the inlet side of that scoop in order for it to work properly. What that does is, let's say the water's coming out of the boiler, it hits this elbow and the flow gets all turbulent and all the dissolved gases get spread throughout this, 1 inch cross section of pipe. It takes 1.5 feet of straight horizontal flow for those lighter than water molecule oxygen molecules to work their way up towards, the upper portion of the pipe, so that when it enters the scoop, it can be scooped. It'll turn back into a bubble and it'll be scooped. Now, that said, how many of you have seen these things installed with, oh, I don't know, a close nipple right here, or even a street 90? At that point, we have a very ineffective air separator. What we have is an expensive coupling. All right, so that's very important when it comes to scoops. Now, why would you use a scoop instead of a 4900? Well, the cost is considerably less. That's one thing to consider. If you have the room, if you have the 18 inches of real estate where you can run an 18-inch run of pipe, here you have a very inexpensive and very reliable alternative. It's something that you could do if you wanted to, right? If you have the real estate. More often than not, however, we are tasked with cramming, 10 pounds of hydronic, into a 5-pound closet, and maybe that 8 inches doesn't exist, maybe, or that 18 inches doesn't exist. We can't do it. So then we might be able to, then we would have to use a high performance air eliminator. Okay, let me know if that makes sense in terms of an application. They work real well. They do an excellent job of controlling air. It's simply that you have to have the room. If you have the room, then we're good to go. All righty.
A question came in, is that can you have too much pipe in front? Not at all.
No.
Nope.
Not at all. This is the minimum that you're looking for, so you get that laminar flow, so it has a chance to scoop that air out. So you go longer, you're going to have still laminar flow. The flow remains the same once you get over that 18 inches. Yes.
Yeah, it's not going to get more laminar. Yeah.
Some people will say 12 to 18 inches. If you start looking at bigger boilers and bigger pipe size, you might be able to shorten that length as you get larger. If you're looking at 2, 3, 4 inch pipe coming off your boiler, you might be able to drop that down a little bit if you wanted to. So, but 18 inches is going to say, hey, you know what? You're going to guarantee to get that laminar flow at that point.
Very good. All righty. Good stuff. Let's take a look at the 4900 now real quick. And the 4900 is, it's very similar to the spirovent or the Honeywell or many others it doesn't just remove air, it kicks air out of the club, it closes the door behind it and says, don't ever come back, okay? It basically blacklists air, it says get out and stay out. It can remove air faster than you can put it in many cases, okay? It's high performance air removal. Now that removes 3 times more air than a spirovent. Isn't just marketing speak, there's actually a little bit of science behind it, and I'll explain how it works. Again, what you have here is a big open space in the piping. Our open space in the piping, everybody has a medium for removing air, some sort of a medium. In spirovent, it's like a little pipe with what looks like little copper brushes on it, all right? And there are various other ones. Ours are these little Paul rings. They're little, very small, computer-designed stainless steel rings that act as a collision type of medium. What happens is this: on the inlets, you have the water with all these micro bubbles and mini micro bubbles and mini micro bubbles entering the big open space in the piping. As the water goes into the basket here with the Paul rings, these Paul rings, through the coalescence effect, will collect the mini micro bubbles, the molecular oxygen. It'll start to glom onto these Paul rings. All right. And as the mini micro bubbles get bigger and bigger and bigger, they will eventually, because the velocity is so slow, they'll go glug, 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 glug up into the upper portion of this chamber, push the float down and go out the vent. Now, the reason this will do 3 times more air than a spirovent, there's no magic formula here other than with these Paul rings, we have 3 times more surface area than that brush thing to gather the mini micro bubbles. All right. So spirovent does a really good job. This does a really, really, really good job. So there's, one isn't, it's just, there's different levels of really good here. All right. The upper portion is removable and serviceable if necessary. And another neat little thing about it here, there's no minimum pipe run, obviously, no minimum pipe run required on the inlet side. So if you don't have that 18 inches, this is the ticket right here. Okay, there's no minimum pipe run. There's no problems with glycol or anything else. And those Paul rings work to maximize the air removal. Just another little feature for you to recognize is right here. It has a built-in set screw that can actually close this thing or shut it off. If you're the type of installer who likes to pressure test their systems with air before filling it up with water, what to do about a spirovent or something like that's always been a little bit problematic. Well, this has a little set screw that you can close. You just turn the screw and you close it, and now it becomes an air keeper inner, and it'll keep the air in until you have finished your air pressure test. But then you have to remember to open up the set screw in order to turn it back into an air letter outer. All right, but it is a nice little convenience item. All right, Dave, anything more you want to add on the conical shape and the operation of this?
One of the things that's nice about that is when we see a lot of failures in vents, it's because it's the high point of the system, or you still have a separation between water and air. And at least here, what we have this conical shape, which is going to make sure the mechanism that you see, that the valve mechanism is going to stay in a little bit of air, that we don't get the oils and we don't get the garbage that's floating on top between the separation between the water and air. So you don't see these things getting stuck open. And I'm not saying you're going to see water come pouring out of it. How do you know a vent is stuck open? You usually see it on year 2 with the big old crust coming out the vent itself, right? So that means we're starting to see a lot of crap inside of those things. So when we do this cone shape at the top there, it's going to keep the mechanism in the air so it doesn't see all that oils and dirts and whatnot that we have in the water itself. So make that thing last a heck of a lot longer. And that's also why I consider even your basic vents back on your scoops, keep that little valve closed, right? The little cap, keep it closed. Open it once a year, let the air come out, right? If you close it, the air stays there. It doesn't go back into the system again. And if you open it once a year, good to go. New install, I would say leave it open for that first year. So this way you're not seeing these vents always getting corroded and getting replaced, right? I think everybody makes sure they have on their truck an expansion tank, a vent, right? And a PRV, both PRVs to replace on every job, right? Because they see them crusting up, they see the expansion tank, nobody's touched it, nobody's looked at it for years. So that's my opinion. I know a lot of people say they'd rather keep them open all the time, and that's fine also. So there's a lot of different ways you can do it, but just remember all those oils that you got floating in the water is going to gum those things up.
Very good. Excellent. All right. Thank you, Dave. Dave's not here, man. Very good. All righty. Let's finish up our discussion then today on this thing called the point of no pressure change. I got an email from one of you guys. I'm sorry, I don't remember who sent it, but it had to do with circulator location, pumping away, etc. And I want to make sure we're talking about the right thing. The point of no pressure change is not the air separator. That is not the point of no pressure change. The point of no pressure change is the point in the system where the expansion tank connects to the system. It happens to be in many cases at the air separator because the air separator has a convenient little tapping for it, but it's not specifically the air separator. It's the point where the expansion tank connects to the system. That's known as the point of no pressure change. Now, guys, if we were to call something the point of no pressure change, what would we expect to happen to the pressure at something called the point of no pressure change? What would you think, Dave, Rick? If we call something the point of no pressure change, what should the pressure do?
Never change.
Not change.
It should not change, right? If we go to the trouble of calling something the point of no pressure change, it is perfectly reasonable and logical to expect that the pressure of the point of no pressure change doesn't change. Why else would you call the point of no pressure change the point of no pressure change? But I'm going to suggest to y'all that the pressure at the point of no pressure change does change, and it changes all the time. If the pressure at the point of no pressure change does change and it changes all the time, then why in heck would we call the point of no pressure change the point of no pressure change? That doesn't make any sense. And how many peppers could Peter Piper pick if Peter Piper could, in fact, pick a peck of peppers? I can tell you're stunned. Why is the point of no pressure change called the point of no pressure change? It's not that the pressure doesn't change at the point of no pressure change. It does. It's called the point of no pressure change because it's the one place in the system where the circulator can't change the pressure. The circulator can't change the pressure. Now, we call these things pumps, but they're really circulators. There's this technical difference. But technically, I think we could call a circulator a pressure differential machine. Its job is to create a pressure differential in the system, and then Mother Nature takes over. High pressure goes to low pressure, right? So its job is to create a pressure differential. The point of no pressure change, where this thing connects, is the one point where the circulator cannot change the pressure. It has no impact. Why is that? Well, let's take a look here. Let's take a look, okay? There's only three things that can change the pressure. Only three things can change the pressure. All right, I've got water on that side and I've got air on that side. One way to change the pressure would be to either add or remove water from the tank. Can the circulator, while it's circulating water across this run right here, can the circulator be so powerful that while it's doing its circulating thing, all right, it's also jamming some extra water into the water side of the tank? All right, I got that backwards, didn't I? That doesn't make sense. That's the air side. That's the water side. There we go. Rick, I'm surprised you didn't catch me on that.
I just let you go, man. Otherwise, I'll be interrupting, you know.
You interrupt all you want. The reason right here is to reel me back in. All right. Can the circulator, is there a conceivable way that the circulator, while it's doing this, can also jam some more water back into the water side of the expansion tank? Well, no. Where would it get it? Here's a couple of truths about hydronic heating systems is how much water is in the system? It's a fixed amount, all of it. There's no extra water. In order for this circulator to not only circulate a certain amount of gallons per minute that way, but also jam a few extra, ounces of water into the water side of the expansion tank, it would have to get that water from somewhere. Where's it going to get it, right? It can't take it away from any place else. What would it leave behind? It can't leave behind. A vacuum. There's no air in there to begin with. So it's a fixed amount of water. So it's a zero-sum game. I cannot put any water into that tank so that it stays there. All right. And by the same token, could I have this water moving so much that by some sort of a Venturi effect, I'm taking water out of the tank? Well, it's no for the same reason, right? Where would I put it? The pipe's already filled with water. In order for me to take water out of the tank, I'd have to put it somewhere, and there's no room for that extra water in the system. It's already filled up. So when the circulator's running, it can neither add nor remove water from the tank. All right, does that make sense? I want to make sure that makes sense to everybody. It just simply can't do it. It's impossible. On the other side, another way to change the pressure at the point of no pressure change would be to add or remove air from the air side of the tank. And a circulator obviously can't do that. It doesn't know how to use a Schrader valve, okay? And the third way is actually kind of linked to the first way, if you will, is you heat up the water so it expands. And what does it expand into? Oh, the expansion tank. How clever. All right. That will add and remove water from the tank, but the boiler heats the water up so it expands, not the circulator. So as far as the circulator is concerned, this spot right here is the point of no pressure change. It cannot change the pressure at that point. Does
Can I
that
add
make
something?
sense to you all? Yeah, go right ahead, Rick.
One thing that's important too, that on a lot of these pictures that we see that are sent to us and a lot of designs we see that are detailed, they're not showing a pressure gauge in that area right there. They say, see where it's down on the boiler? And that's fairly close, but the most important place you want to know where the pressure is in the system is at the point of no pressure change. So the only reason boilers have tridecators on them, Thur altimeters way back when, is because the codes in North America were forcing them to put them there. Realistically, the pressure of the system wants to go right where John was pointing at. I can't point there myself, but if we could put a gauge right past that pressure reducing valve so we could see what the pressure is at the expansion tank, also known as a point of no pressure change, that would be a good spot for it. So anyway,
Yeah.
that's a pet peeve of mine. All my sketches, I show it on there, but that's where we really want to see what's going on in the system.
And the other thing you'll notice is the pressure reducing valve actually connected to the system at the point of no pressure change. So we can't accidentally open it up by some sort of fluke with the circulator changing the pressure in the rest of the system, which you can see happen. So to whoever, if you're still in, and I apologize, I forgot your name, about the point of no pressure change and where the circulator should go in regards to the air separator. Again, we're not so worried about the air separator. It's here. It's right here. Is the point of no pressure change. And we like to pump away from that point of no pressure change, as we'll see in a second. But I just want to show you what can happen in the system, okay? What can happen within a system. Now here we have, this is just a drawing of a system, and we've taken out everything that doesn't matter, like the boiler, okay? And forget that this is a horizontal line. Let's presume that this point right here is the highest point in the system, and that is 18.5 feet above my point of no pressure change circulator location. All right, 18.5 feet divided by 2.31 comes out to 8 psi. So the pressure up here, simply by static pressure, all right, that's the height without the circulator doing anything, is going to be 8 psi lower than it is down at the point of no pressure change, down at the bottom. So if my system is filled to 12 psi and I have 12 psi right here, and my circulator is off, and I had a gauge on the Gazinta and the Gazouta side of the pump. Now the circulator is not creating any pressure differential then, so those two gauges should also both read 12 psi. Now way up here at the top, it's going to be 8 psi lower. That should read 4 psi. Everything's off, and here I have the pump pumping towards my point of no pressure change. All right. So what would happen when the circulator turns on? All right, I still have 12 psi at the tank. This circulator is capable of creating, in this example, it's capable of creating 4 psi worth of pressure differential. That's around 9 feet ahead or thereabouts. All right. When that circulator's on, since I'm pumping towards the point of no pressure change, this gauge can't increase. All right, all we're doing is creating a pressure differential. We're not creating a pressure boost, we're creating a pressure differential. Since I'm pumping into the point of no pressure change, the pressure on the Gazouta side doesn't change. The pressure on the Gazinta side, however, on the inlet side has to drop by that 4 psi. I'm creating a 4 psi pressure differential. The circulator's doing its job as far as it's concerned. All right, but the pressure on the inlet side right here is 4 psi lower, and it's 4 psi lower here, and 4 psi lower here, and here, and here, and here, and here, and most importantly, right there, it's 4 psi lower. It was 4 psi, now it's 0 psi. If I have 0 psi, if I have no pressure, can I have a pressure differential? Well, no, I really can't. If I don't have a pressure differential, what else don't I have? Well, I don't have flow. If I don't have flow, I don't have heat. And if I don't have heat, I don't have a happy customer. If I don't have a happy customer, I don't have a happy life. All right. So you get that call and said, hey, pal, I got no heat. What's going on? You run to the job site, okay, to do your troubleshooting. And you see the boiler's boilerating and the pump's pumpulating, but the thing ain't heaterating, right? So you put your hand right here, all right? And the pipe's really, really hot. Okay. And you put your hand right there, and it's not so hot. What's your first reaction? What's the first thing you're going to conclude? Well, that's what an air-bound loop looks like, right? It's clearly air-bound. So I'm going to get my hose out and I'm going to purge that line. And you'll purge that line, okay? Will you get any air out of the system? No, you won't. Why won't you get any air out of the system? Well, it's not an air problem. The number one indicator, write this down, the number one indicator of an air problem is air, the existence of air. If you put your hose on there and you try to bleed it out and no air comes out, stop it. It's not an air problem. It's a flow problem. Flow problems look a lot like air problems though. And here's the kicker. You put a hose here and all of a sudden you've created flow now. What you're going to very temporarily solve the problem, okay? You've allowed it to create a pressure differential. So the water's going to come out a little cold, but really, really soon that water's going to come out hot. And you're going to say, oh, I lick that. You roll up your hose and you leave, but you don't get 20 feet out of the driveway when you get a call back and say, hey, it's not heating anymore. And you got to go back and try and bleed it again. And you bleed it again until you realize, this isn't going to work. I can't keep bleeding this thing because this air is particularly sticky, but it's still, the thing is, it's not an air problem. It's a flow problem. It's a flow problem. Now, what you might do is if you're still convinced it's an air problem, I've seen a lot of guys put in an air vent up here. We're just going to let that air out automatic, so I don't have to keep coming back. Is that going to solve your problem? No, why not? It's not an air problem, right? It's not an air problem. So what do you do then? Well, then you think, oh, maybe I misdiagnosed this. It's not an air problem. It's a pump problem. How do you solve a pump problem? Dave, how do you solve a pump problem?
Make it bigger. He's muted.
He's muted. Good. That's a good thing for Dave.
Yeah, put a bigger pump in.
Yeah, you're like Chief Brody in Jaws. We need a bigger boat, right? You got to get a bigger pump. So you go down to the wholesaler and you buy the BFC 9000, okay? It's the Tasmanian devil of circulators. It doesn't come in a box. It comes in a freaking cage and you have to use special gloves to install it. And it can do 12 PSI worth of pressure differential because we're going to ram the water the hell through that pipe whether it wants to go or not, quite literally kicking and screaming. Well, have we solved the problem? No, because we're still pumping in to the point of no pressure change. And because we've so thoughtfully put an air vent up there, Rick, air vents go both ways, right? They're air letter outers, but under the wrong set of circumstances, they make pretty good air admittance valves too, don't they?
AC/DC, baby.
That's it. That's it. So you've got an air vent that could be an air letter inner now, and now we've created a vacuum. Now we have air problems, and now we've really messed this thing up. All right. So we've got to figure out a way to fix it. Here's the kicker though, gang. This just doesn't develop over time. This doesn't develop over time. This is almost always, it either does this or it doesn't, okay? This is almost always the result of a specific act done by someone. And the thing is, I'm sure all of you guys have seen old systems out there with the big old B&G 100 or the Takeo 110 on the return side of that boiler, right? And it's been sitting on the return side of that boiler, and that thing's been working fine and dandy for 45, 50 years, right? It's been chugging along, heating just fine. The problem with pumps that old is eventually they kind of die and they need to be replaced. And what are they replaced with? What most people keep on the truck for service, because that's what somebody told them to keep on the truck for service. Hey, keep this 3-speed pump on the truck for service because it's the only pump you'll ever need. It does everything. It doesn't have 1 speed. It doesn't got 2 speeds. It got 3 speeds, man. Low, medium, nobody uses those. You just go right to high and everything's good, right? So you put a 3-speed pump on there, you've changed the dynamics of the system. That old B&G 100 was a very high flow, very low head, very flat curve pump. All right. not a big PSI pressure differential animal. You put on a Grundfos 1558 or a Takeo 0015 or a B&G NRF 22, or pick your favorite flavor of 3-speed. You put that on the return side, that is now a much lower flow, much higher head, higher pressure differential pump. We've now created a problem where there wasn't one before. All right. So how do we solve it? Well, there's 3 ways to solve it. To me, the simplest thing, the easiest, fastest, least expensive, and most certain way to fix that problem is going to be to take out the wrong circulator and put in the right one. That's going to fix the problem, and it's going to get done fast. To me, that's the easiest way to solve the problem. A lot of guys will say, well, wait a minute, why don't you just move the pump from here over to here? That'll fix it, right? Oh, hell yes, but you're repiping the freaking system now. You know, absolutely it'll get it done, but you didn't have a problem before you tried to put that pump in. So now we're just gonna cut butter with a chainsaw here and really overcook it. You don't need to do that. You just simply need to replace that pump that's the wrong pump with a pump that's more appropriate for the application. Again, least expensive and fastest solution. Another solution might be, well, why don't I just raise the fill pressure? You could do that. You sure as heck could do that, but to what? You're guessing, right? And guessing, when you guess, one of 3 things can happen, and 2 of them aren't good. Okay, that's just the way guessing is, right? That's why it's called guessing instead of knowing. If you know, 1 thing can happen. If you guess, 1 of 3 things can happen, and 2 of them are bad. What do you set it to? You guess, right? And then you got to fill everything up and try it. All right. And if it's an older system, you got to drain the system. You got to, whatever you do to the fill pressure, you got to do to the expansion tank, right? And you can't add pressure to the expansion tank while it's under pressure, right? So you got to drain that, add pressure to the air, to the expansion tank, change the fill pressure on the fast fill valve, fill it up, purge it, bleed it, get all that stuff done, and hope it worked. Because if it didn't, you got to do it again, and then you got to wait till the thing heats up all the way to see if you're approaching that 27 psi in the expansion tank. At that point, it's easy to just take out the wrong pump and put in the right one, in my opinion. At that point, just keep it simple, right? Keep it simple. Alrighty, and just for giggles and grins, here's the circulator pumping away from the point of no pressure change. If you're replacing a boiler and rebuilding the pump tree, or it's a new installation, always, always, always pump away. You just avoid all of those problems, right? Here we're adding the circulator's pressure differential to the system. We're keeping the pressure up all the way through the system. We're controlling the air throughout the system a little bit better, and we're going to have flow, and we're not going to even entertain any of those issues. And the reason this is really the way to do is basically because of what we call Henry's law. The higher the pressure on a fluid, the more gas is dissolved in that fluid, and vice versa. So more pressure we keep dissolved gases dissolved in the fluid. We lower the pressure, the more those gases want to come out of solution. Shake here. Well, I got a bottle of seltzer here, but you get the idea, right? Okay. Right now it's all kind of fuzzy, and right now the bottle itself is kind of stiff, and you can see all those bubbles are starting to dissolve. What we're doing is we're increasing the pressure on the fluid. If I open this up and see, I've already had most of it, so it's not going to go everywhere. Watch what happens when I take the pressure off. You're going to hear it there, and then see the bubbles come back. All right, that's Henry's law in a seltzer bottle. All right, so when we keep the pressure up on the fluid, we keep dissolved gases under control. And again, colder liquids hold more gas. Hotter liquids, the gas wants to come out of solution. So air separator on the supply where the water's the hottest, right after the air separator, bam, the pump, any dissolved gases that are left over, wham, go back into solution, and we get nice flow throughout the system. So that's why we pump away, people. That's why we pump away.
Got one for you, though.
Yeah.
How about all those boilers that the manufacturer is showing that you're supposed to pump into the boiler on primary, secondary?
Say that again.
So the manufacturer of the boiler wants you to pump into their heat exchanger. The point is, John's already brought it up, but it's worth repeating because it's come up several times in questions that they'll look at a drawing, one I put up there, somebody else puts up there, and they say, that doesn't seem right for whatever reason. So I guess my point is, we're you're going to pump, if you're forced to pump into the boiler, okay, that's on the return side, right? And so you might you want to reconsider putting the air separator, air scrubber on the return side. We want it on the hotter side. The point is that we oftentimes will separate those two. People get locked in on saying that the makeup water, the expansion tank and all the other apparatus belongs on the bottom side of the air separator. Not necessarily. Sometimes they want that air separator up in the hottest water, as John's already talked about. Then we're piping the expansion tank and the makeup and everything at the point of no pressure change, which is where the pump going into the boiler is going to. So I'm just making sure you don't get locked into always seeing that same setup on the air separator. Anyway, that's come up several times in questions. I thought I'd just make another note of it.
Very good. Excellent. All righty. Cool. Okay. Well, that we kind of went a little long there, but it was kind of fun to talk about. Now let's talk about that Takeo trivia question answer. What did Johnny Fever say to get fired from his job in LA before he came to WKRP? And you see it right there. He said booger. That's what got him fired from Los Angeles.
Little
He's listening to
suggestion from
music.
Tim Ward. Little fog hat right now.
Little fog hat. There you go. But he said booger. Someone had just said jive ass. Early in the first season, he was rehired back to a station in Los Angeles, and he got fired for saying jive ass. But that's not what he got originally fired for. Originally fired for saying booger. All righty. So that's our Takeo trivia answer for this week. And Dave, do you have everything set up to pick the winner for last week?
I do.
All right, I'm going to turn this over to you. Oops, sharing, there it is. I'm going to make you the presenter here, Dave. Are you ready?
I am. Let me
All right.
let me put that up on the screen. So from last week, what was the question from last week?
From last week, the question was, which actor played the same character in both the movie version of MASH from 1970 and in the TV series of MASH? Which actor, what was the name of the actor and what was the character? And that was, of course, the actor was Gary Berghoff, who played Radar in both the movie and the TV show.
All right, so these are the names that got it right last week. So let me tap to win.
Round and round she goes, and where she stops, nobody knows.
Yes, I win, finally.
I don't think so.
Oh, man, I got this pile of stuff. I always have to give it away. All right, we'll do it again.
Looks of things, you've got a nice little pumping away station set up right behind you there, don't you, Dave?
I do. Got it all ready and set up to rock and roll.
All right. Oh, Dennis Suave Last is our winner.
All right, Dennis.
Very good.
Excellent. If you can, Dennis, I know I've got your email, your mailing address, but if you can send it over to me again in the chat section, I will make sure I get you out our gift pack again. And also let me know a t-shirt size for you. I've got t-shirts this year, so please let me know.
What's in the gift pack there, Dave?
Good to ask. Well, one, I've got these great coffee mugs that we end up leaving on most water heaters. I've got them all set up with Takeo After Dark on the backside.
Oh, nice.
Good.
Let's see, what else do I got here? So we've got our t-shirts. So this one, nice black t-shirts, embroidered. So it's not going to wear off in a couple of washes.
None of that silk screen nonsense. We go all the way, right?
That's right. That's right. So we got some PPE. I've tested them all out.
Oh, gross. Oh, gross.
The couple of screwdrivers that we can never find on the truck. You got 10 of them out there. So I got the Phillips and a straight bottle opener. Nice little Takeo bottle opener there. A couple of the pump stickers. So if anybody ever wants any of these things, let me know. I've got some of these. I got a pile. Whoop, that's upside down. So find me on Instagram at Takeo Training. Send me a message. I'll send some out to you. I got some Takeo After Dark ones also. A couple of koozies. Got a nice ball cap. And last but not least, there's the Takeo After Dark stickers also. And I also have this Bluetooth speaker that you can run on the job sites too, instead of just listening on to that little speaker that comes out of your phone. So that is the prize pack that I'm giving away
Nice.
tonight. So Dennis, good job.
Very good. So bone up on your trivia, people, now for next time, all right? Excellent. Very good. Very good. All righty. So we're coming back here. Let's see what we got. So that's today's program. Oops, here we go. Next week we're going to be talking about we're going to get into circulators and circulator selection and what, figuring flow, figuring head, and what does it mean? And I'm going to suggest to you right now that one of the things we've learned with variable speed circulators is that the circulator really has more to say about overall system efficiency and overall system performance than we've ever given it credit for, to the point where we have a chronic overpumping problem in our industry because we don't know how to size pumps.
Yeah.
We size pumps for convenience and not performance. We size pumps not for the job. We just say, hey, I want a 3-speed pump, turn it to contractor, no callback mode. I'm going to get the hell out of here because it works. All right. There's a difference between it works and it works right. There's a big difference. Or as Jeff House would say, it runs, but does it work? There's a difference. If all we want to do is keep people from freezing to death, that ain't that hard, man. That ain't that hard. But that's not what they pay us for. As professionals, we are charged with putting together a system, which by definition, the system is something in which the whole is greater than the sum of the parts, but the parts are purpose chosen for that system, meaning the circulator sized for the application. It's sized appropriately without being too large. We'll show you next week what happens when that circulator is too large and how it can dramatically impact the performance of the system, the efficiency of the system, and the life of the system. So it's kind of important stuff, man. And that's what we're going to talk about next week. All righty. And then now that's it, man. I guess we're kind of done. We're going to see you next week. But as always, we'll stay on for as long as you guys want us to answer whatever questions y'all might have. So
I'm also gonna demonstrate the pumping away display that I have behind us too, so you can actually see it. I mean, everybody looks at John's screen and says, "Yeah, well, you made that screen, so of course you're gonna make it look like you do what you want it to do." No, I've got an actual demonstration here too, so we'll fire that thing up too.
Okay, very good. Let's take a look at it, David. We got everybody up here. Why don't Rick, you and I close our webcams, and then Dave will have the whole screen.
Well, I'm also moving the camera a little closer.
Rick, yeah, there you go.
Well, you still have the slideshow up too.
I do?
Yeah,
No,
I see. Yep.
Oh, I gotta.
Quit. There you go. Oh,
okay.
Nope. Go back again.
No?
Now you got a blue
I don't think it can make it completely go away. But if you're on your PC watching this, you can always just click on my camera and it says enlarge and you can blow it up so you can actually see everything that I have here. So this display I made earlier in the spring since we were stuck home. I had one up at the factory. So we made another one here. And what I want to show you is I have a circulator 006E3. I use the 6E3 circulator because it is a composite volute, so I didn't have to worry about rusting out the water that's in the system itself. It is pumping in this direction here, so I've got a gauge on the discharge. I've got one on the suction side. We come across, I run a T here with a valve on either side of an expansion tank. So behind the expansion tank is just a threaded T that I have thrown in here. Then I come up over on this side, I've got a balancing valve. Whoop, you can't see that valve. So we got a balancing valve over here. This, imagine now as your heating loop in the system. I threw a 4900 separator up here. Yes, I'm pumping into it, but hey, I'm only doing this much amount of pipe here. So, and then it comes back down on the return side, got a drain valve over here. So right now, with this valve open and this valve closed, we are going to be pumping into the expansion tank, right? So just imagine this as that T hanging off of there and pumping into the expansion tank. So when I kick this circulator on, what I want you to pay attention to are the pressure gauges. All right, so right now on the discharge side of the circulator, we're looking at about 19.5 PSI. They are a little off, okay, which is understandable. That's what happens with pressure gauges. It'd be better if I had one single, but then you couldn't see the differences. And then on the suction side, we are just about 20 here. So let's kick this circulator on. And I'll wait for it to refocus. And what do you notice on the gauges? All right, we're going to see here on the gauge on the discharge side is what we talked about before. It is still just under 20 PSI over there. But the suction side dropped. Pressure differential machine, it's got to create a differential pressure. So the pressure is now dropped on the suction side, and now we're looking like at about 17 PSI on this one here. So that's what we see when we're pumping into our expansion tank. So let me turn the circulator off. I'm going to change the valve position. So now I'm going to close off the expansion tank from the discharge side of the circulator and now open it up to the suction side. Simple as that. And now we're pumping away from our expansion tank, as you can see here. So when I click it back on again, what we're going to see on the discharge side is that our discharge pressure is going to increase, and now we're up to about 23 PSI. But then on the suction side, it still stayed as the system pressure itself. So doing what it's supposed to do, doing what we wanted it to do in the first place. Again, if you had a flat curve circulator, pressure differential was really small, we're not going to see it as much. All right. And it may not become that big of a deal as John was talking about. Make sure you have that flat curve 007 style circulator in there if you're still on the return side into the expansion tank. But here you can see now you've got the circulator doing everything it's supposed to be doing.
Hey, Dave.
Yes, sir.
Let me comment on one of your comments. It was almost like you were making apologies for pumping into the 4900. It would only be a problem if you were hooking the expansion tank up to the bottom of that. It goes back to the point I made earlier. There's no problem pumping into a 4900 or an air scrubber of any sort, as long as that's not where the expansion tank is hooked up to. Anyway.
Correct. No, I like it.
Nothing wrong with that.
Yep. No, I didn't think I was talking about it like that. So I was just out of what was I saying? Out of habit of always saying pumping away, but pumping away, we always say pump away from there, but yes, exactly.
Yep.
So
it's a beautiful thing.
Any other questions that you can see there? This is a very simple little device that you see how this thing is all set up.
Yeah, and it shows it beautifully.
So I do have to say thanks to my buddy Mike, who helped put it together for me one day. He had some of these parts and pieces on his truck. You don't find too many half-inch or three-quarter sweat by half-inch MPT tees laying around, cast tees that we put into the back there. And this balancing valve, man, what a pain in the neck that was to find out there. So he helped me put everything together, and I threw it up on the board here, ready to rock and roll. Unfortunately, the one that we had at the factory was given to us by Dan Holohan, and it was given to him by Amtrol. They had built a suitcase out of it, and it had clear PVC pipe on it with a small circulator, and same idea with the setup on here. And once we went into lockdown, I called up at the factory to anybody that was happened to still be walking into the building, and they said, "Oh yeah, we'll get it for you." So they pulled it out of the storage room and then shipped it down to me UPS. But as you can tell, with 25-year-old PVC pipe on a UPS truck, didn't last too well. So, so if Dan is there or Dan hears this, sorry, man, I had to rebuild it. So I greatly appreciate it. We had it for a bunch of years at the factory. So we were using it for a few years up there, and then unfortunately I killed it. So
it's so funny when we always talk about this in class. There's always a couple of guys that say, "Oh, you got to prove that to me." And I said, "Well, we don't have to prove it at all. We don't have to prove it to you because we didn't come up with it. This is they've been known. The Homer Thrush developed the very first centrifugal pump back in the 30s. I'd say about a month after he developed the first centrifugal pump, somebody figured this out. All right, so this has been written about, for decades. The point of no pressure change and pumping away, et cetera. That's been known about forever. But it's still, will get guys really don't get it until they actually see it. When they see it, they got it. They make you do it a couple, 3 times, don't they, to say to just to prove that it wasn't a fluke. So it is kind of it's an interesting phenomenon. There was a question here from Randall. How you doing, Randall? Is Takeo building prefab boards with zone valves, expansion tanks, scoops, zone controls, etc., for high efficiency boilers? We have a distributor providing them locally using Takeo products, minimum 2 zones and up on diamond plate mounting boards, and that's FW Web that's doing that. We don't make those, and that's something we've always wondered if it's something we should make, but we don't offer those. I guess this is a good question to ask. And Rich McGrath says HTP makes those as well. Is that something that if we made it, would you buy it? Because we've got a very people like to do stuff themselves. I can remember when all 3 of us worked at Wurzbo and we came out with those pro panels, right? Rick, what was the one thing everybody said about pro panels that you were?
Well,
that
they
you
loved
recall?
them, but they were too much money.
They were too much money, and they figured I can make that. I had a guy actually tell me I can make that for less money than that, and I said, great, let's hire you to do it. And then all of a sudden he backed off.
Yeah.
But people don't want, time and money are interchangeable, right? You can always save more of one by spending more of the other. So if something like that is prefabbed, hang it on the wall, and you're good to go. If that is of value, I'm sure that's something we can consider. But I just take a quick poll here. Is it something you guys might find useful? Is it something that you would actually buy?
Another argument that I heard one time is you're taking the art away from me. I like building the Starship Enterprise on the wall, and you're taking that from me. And I was like, no, I'm not. You just go ahead and do that.
And nobody said you got to mount it crooked.
Yeah.
But I always look at that and I say the value of you as a contractor isn't in your ability to put this stuff together.
Yeah.
It's your ability to make sense of it, understand it, and apply it properly. Like I said, putting pipe together is not that hard. Putting pipe together attractively is not that hard, although some people make it look like it's impossible. Your ability to make sense of it is what your value is. Not to mention the thing you as a contractor, the widget you have to sell is 1 hour of time, and you have a limited inventory. So do you like the hobby of creating a piece of art? Well, that's okay. That's your business model. That's how you're choosing to do it. But it's more hobby than business. If you're doing this because you want to install good jobs, do the job the right way, but also maximize your inventory of widgets to sell, maximize your billable hours, well, there's got to be a swap in terms of convenience versus, art, I guess.
Yeah.
Does that make sense? Is that said the right way, guys?
Yeah. Randall's got a good point. I mean, if you got a shop that's set up where you have somebody that's a prefabricator, somebody who's just, you pay by the hour, they're really fast, they do a good job. You could build that panel in your shop, take it and hang it on the wall. Your labor, the installer's labor is cut, tremendously. Then yeah, it pencils out. And Randall Hobby's making a point on that. And that's we got to, I'm in Salt Lake City. We're right on the edge of the mountains here. We're closer to the snow than anybody else. And there's a bunch of people doing multi-million-dollar, 12,000, 15,000, 25,000 square foot houses with, trophy homes, basically. And the contractors around here all kind of got it down. They build everything in the shop. They take it up and hang it on a wall.
Right.
So yeah, that there's a method to that, and you could make money and still be competitive, etc. So
yeah, we got one guy we know has a retired pipe fitter, comes in, 20 hours a week, spends half a day every day building these panels,
yeah,
custom built for each job, and then when it's time, it goes to the job. And it's the same idea. It's just somebody, who's doing the grunt work, and it's piped, it's wired, it's tested, it's complete, it's ready to go. And that's to me, that's an interesting question. I'm not entirely.
It all depends on how busy you are.
Yeah.
really what it comes down to. Do you have the time to go build it? Do you have the time to go put it on the wall and get to the next job because the phone's ringing off the hook,
Mhm.
right? To the end user, it's going to cost them the same.
Right.
That's the
Right.
way it's they are not spending any more money on it. What you've got now is somebody sitting there staring at a board and say, hey, let me fit all these parts and pieces on this board, rather than you staring at the wall saying, where am I going to put everything? And then
Right.
it becomes cookie cutter in a way. So that's what some of the wholesalers are doing. That's what Web is doing. They're making them cookie cutter in a way. If
Mhm.
this is what you got, here you go. There were some companies out there that make them custom for what you need, which is cool too. You give them a design that you're looking at, they'll build it for you. You can pop it on the wall, call it a day. Do the thing that, mess around with a thing that makes fire and can explode and stuff like that. You mess with that.
Right.
Sometimes just putting a couple of pieces of pipe and pumps and doing some of the wiring. Yeah, it's fun. Yes, we enjoy it. Yes, we're freaks like that. It all depends on how freaky you want to be.
Right. And again, if you have a hobby or a job, it's a business or a hobby. It's
Yeah.
really, my opinion. I hate to be that blunt about it, but that's what it comes down to.
I think it's
The
also,
best job, the most profitable jobs wind up being materials heavy and labor light.
Yep.
Those tend to be very profitable because you're making, the bottom line numbers, the bottom line number is not going to change. But what would you rather be? Would you rather be labor heavy and materials light, or materials heavy and labor light? If you're materials heavy and labor light, you free up time to do another job or two or three or four. Yeah.
right. Or you're looking at yourself as a two-man shop, and all right, I'm getting so busy right now. Do I hire another guy?
Mhm.
So now you start looking at the financials. Can you afford to hire somebody, keep them as busy, or do you eliminate some of the labor and keep it as a two-man shop? So that's where you start breaking that edge, and you got to make sure it works for you. Exactly.
Right, right. And then every guy's going to be a little bit different. It's your business, so you do it the way you think is best, obviously. All right. Everybody's from Missouri, says Richard. Oh, you know that. I think that's what you meant anyway. What else you got out there, folks? Any more questions? Yeah, we're down to 55 of you out there, plus us. So any more questions you guys have, please? Oh, here we go. Philip May, can you recommend where we can get an accurate gauge set up to measure the PRV pressure? An accurate gauge set up to measure the PRV pressure. I'm going to throw that one to you, Rick. What do you think?
I just, again, go back to what I was talking about, where the gauge actually belongs, just past the pressure reducing valve, just prior to the point of no pressure change. I think it's Therese is the brand, and there's a bunch of good brands out there, right? But it's just a little 30-pound gauge. I set my systems at 15 pounds so that I can I don't even have to read the numbers. If the needle's straight up, I'm dead on, I don't even have to look at it, right? So 30-pound gauge, 15 pounds right in the middle. And that's what I do. And I don't think it has to be anything fancy. We're not
No.
doing pump, discharge, or suction, so it doesn't have to be liquid filled. I mean, you could probably get a gauge for 15 bucks and do a great job mine's been out there for 15 years. So it's working just fine. So I don't think you have to spend a whole lot of money there. If you're going to do, pump setup and you're going to look at suction and discharge, as Dave already mentioned, it's best to use a single gauge and then pipe them in and put shutoff valves on each side. So I can look at discharge and then I can look at suction separately and just make a note of it. That's when you want the liquid filled, so you don't get the little bouncing needle and things like that. So anyway, more than you wanted, but that's typical.
Yeah. And then the hard thing, I guess, is to make sure it's accurate, right? So you want to put it up against something that pressure wise, and then test it on that.
Yeah.
So I mean, a lot of times I see guys that are just it's got a hose thread on it. You got a little gauge with a hose thread and a cap on it, and you throw it onto any part of the system just so you don't have to necessarily, like Rick is saying, his sitting in his system for 15 years. Well, has it moved in 15 years?
Oh yes, I've seen it move.
Okay, so he messes with it. Yeah.
I've
yeah.
had problems. Plus, when I maintain the system and I start doing things like changing my expansion tank out and stuff. In fact, I just put a 0034E plus in my system because I don't use makeup water in my system. As soon as I got that little bit of water out of that pump. You know, I had isolation valves on each side, but I lost that little bit of water that was in the volute. My pressure gauge dropped. So I had to hook things up and, you know, not purge it, but I had to charge it back up, you know, kind of put the spring on tension and started doing that again. So anyway, yeah, it does move, Dave. It's not frozen. I know where you're
Well,
going
because
with
there's a
that.
lot of them out there that get frozen, right? There's a bunch
Yeah.
that get frozen, and everybody says, "Oh, well, it looks normal." I looked at the gauge that's on the boiler. Well, how old is that one there? Well, it's been there 45 years. You know, has it moved from 12 psi in 40 years? You know,
Yeah.
drop the pressure and see if it goes to zero. If it doesn't go to zero, then that gauge, you know, it's probably messed up still. So you know, so you want to probably calibrate it on something. Not that you're calibrating it to you know that close. You just want to make sure it's going to move on you once in a while.
Very good. Rich McGrath says Calefactio circulator flanges have ports for the gauges on each side, not terribly expensive. So there's, if you do want gauges on the Gazinta and Gazetta side of a circulator, well, there you go. You can
I've seen
certainly
those. Those are pretty cool looking. Yeah.
Yeah, you can certainly do that if you wish. All right. John Messenbrink took off just a little bit ago. Going to have some dinner. Very good. Well, we thank you again, John, and thank you guys from the guys from Mechanical Hub for being with us on this. They really make it a lot of fun. So excellent, excellent. So any more questions you guys have out there? Because you know, we're kind of tired of packing and unpacking up and down the aisle, town to town, up and down the aisle. Maybe you and me were never meant to be.
If this was closer to Thanksgiving,
the
we'd
last
have to
part.
show that episode.
Yeah. Oh, I was thinking of saving this until Thanksgiving and doing the turkey drop, but what the heck, you know?
Yeah. So if you have a chance right now, guys, and if you haven't really watched much WKRP, and there's one scene that I lose it every year, and I have to watch it around Thanksgiving. So you got to look for the turkey drop for WKRP. So YouTube it, go look
God
at
is
it.
my witness. One of the funniest things I've ever seen on television was that right there.
It is a good show. That
Oh
one
my God,
in
they're
particular.
Thanks for that on the spot report, Les. If you're just tuning in, the Pinedale shopping mall has been bombed by turkeys. Film at 11. Yep. I'm not sure what WKRP, I think it was 1510. It was an AM station. It was an AM rock station in the late 70s, early 80s. I think it was 1510 on the dial, if I remember right. And I never worked at a 1510. I worked at a 590. I worked at a 610. I worked at two 610s, 261s, one in Manchester, New Hampshire, one in Washington, D.C. I worked at two 1440s, one in Virginia and one in Worcester, Mass. I worked at a 104.5 in Massachusetts and a 107 point something or other in Worcester, Mass, WAAF. I worked there too. So I'm trying to forget, were there any other radio stations no, I think that was it. I didn't work at any other stations. Yes, friends, I was a disc jockey and a news jockey back in the day. So I was a combination of Dr. Johnny Fever and Les Nessman.
And that's why he loves this so much. Can't you tell, right? He's
Can't
in
you
his
tell?
element totally. Hey, stories about stations. I had a buddy that I worked with in Alaska for many years, and he used to actually he lived in Wyoming, Rock Springs, I think is where he was. And he could actually pick up X Rock out of Juarez, which is where the song I Heard It on the X comes from. Now, who did that song?
I heard it on the X.
Yeah.
I don't know.
ZZ Top.
ZZ
So
Top.
ZZ Top heard it on the X. He's talking about a radio station that had such a loud broadcast because they were in Juarez, right? They didn't have to follow the U.S. rules for how strong your signal could be. So he's in Rock Springs, Wyoming. He's listening to Juarez rock and roll. And of course, the song you guys that don't know ZZ Top and you want to listen to some original early ZZ Top, listen to Heard It on the X.
Heard it on the X. All right, I can put that on the list. I like ZZ Top, but I've never been into ZZ Top, so that we got to.
Understood. Understood.
So now next week we all got to come in nice long beards. You're already ahead of the game, and we'll be the Z boys from ZZ Top next week.
I'll grow mine back out again. Eh?
There you go. God, yeah, I was. I can remember, well, back when you'd actually listen to AM. I had my first car had an AM radio, and that was it, right? And you're driving late at night in the middle of the night somewhere, and all the stations kind of change their patterns. Have you ever noticed when it's the pattern of the antenna signal. If you ever notice when you're listening to an AM radio station, and then right at technically at sundown, all of a sudden you can't hear it anymore. They change the pattern of the signal because there's another station somewhere that has the same frequency. So, oh my God, Santa! Oh,
That's more than Santa, baby.
Wow!
I'm gonna grow that baby back out.
But the cool thing about listening to AM radio in the middle of the night, and I used to do this at home too. I had a little clock radio, and I just, when I'm supposed to be going to bed, I'd be playing with the dial, and you could get stations from, it's listening to stations in Canada. I mean, from Ohio. I'm a little kid in Harvard, Massachusetts, listening to some rock station in Ohio or something like that. In Cincinnati. It was you don't do that anymore. Now we get satellite radio, and everybody listens to the same damn thing. But back then, you actually had local radio, which was just wonderful.
Yeah.
Another part of our past that is gone and will not come back, boys. That's just the way it is.
Yep.
All righty. Well, we've successfully driven a good chunk of our guests away now. So I'm guessing it's probably time for us
Dropping
to
like flies.
No questions. Questions.
No
babe.
questions. No, are you
Hey,
guys
come
just?
on.
Let me ask you. There's 39 of you left. Are you simply enjoying the repartee amongst the three of us, or are you waiting to ask questions? So we don't need to talk. We talk a lot, but just what's 39 of you left? What do you get? Someone come in and say hello. Or
All right,
not.
just trying to think of questions. All right,
Trying
so
to
that's
think of them.
Okay, Randall, thank you for
They
that.
just
There
like
you
turned
go.
it on and walked away. Yeah.
Christopher says any knowledge is good knowledge, even if it is about radio stations, AM radio stations in the middle of the night, I guess. Very good. All right. Rick, how did you get started in this business?
My brother was a plumber, and coming right out of high school, he got me a job as an apprentice, 17 years old, and started hanging gas meters. And I was introduced to a rigid 300.
Oh, fun.
That's how I got into business. So about 4 years of that, and I decided I didn't want to be a plumber, and I got into the sales end of the business, got into retail and then wholesale, and then worked my way up wholesale and that sort of thing. So
Very
it's
cool.
good.
And here he
Glad
is.
I did it. Yeah.
There you go. How about you, Dave?
I started off as a machinist. So that was a family business, building industrial saws for the picture frame and window industry. Started doing that when I was like 12 years old. Never got into, wasn't in the industry, so to speak, working with family and on job sites. I didn't start plumbing until, well, I never started plumbing actually. Went to school. Finally, I'm working in this shop, designing and building machines. So we designed the machines there too. And my grandfather started it. So I said, oh, I should become an engineer so I can work on the inside of the office and design the machines and then come outside and go build them right afterwards, which I thought would have been the best thing in the world. And never had the opportunity to be the engineer there, only because I probably didn't respect the company as much as I should have as a young kid. And I think probably in 10 years, I was about on time about a dozen. Well, they started at 6:30 in the morning. So somebody who's 18 years old with a car, 6:30 in the morning when you start, yeah, that's kind of hard. Because I just got home about 5. So because the bars closed at Long Island at 4 o'clock in the morning, so it was hard to.
Speaking as his boss, he still doesn't show up on time, but that's neither here nor there, right?
So, but go to college, go and study engineering, and started working doing radiant floor heating for a small manufacturer on Long Island called RTI, Radiant Technologies, as their tech support inside design guy. So I started doing that, and Uponor bought them, and then from Uponor, so then RTI closed down. Uponor wanted to consolidate. then moved over to Wurzbo, which then changed to Uponor, and here I am at Takeo.
Long,
So-
strange trip. Yeah.
It is actually how I got into the industry was I'd been out of school already for about 2 years and trying to move back out to Long Island. I was living in the Bronx at the time, and I was working in Paterson, New Jersey, and back at the shop. So I was jumping back and forth between 2 different jobs, and I wanted to come back out to Long Island. And the reason why I got this interview was because the owner of the company used to be a ferry captain on Long Island. And so he knew the type of students that came out of the maritime college that I went to, that we weren't just a bunch of textbook engineers. Not that there's anything wrong with that, but he wanted somebody a little bit different, and he knew the type of guys that came out of that school. And so that's how I ended up getting hired, is because of my maritime background, not because I knew anything about boilers and radiant floor heating, because I didn't. The funny thing is, I said, I never once really looked at my own boiler in my house, because I'm like, that's not a boiler. That's a boiler. It's got to be 2 stories tall. You got to be able to walk inside it thing when you want to clean it. And I did. On the ship, we put our ship into dry dock every 2 years. So, we went in as freshmen to go clean that boiler on the inside of it. So, so I still never really paid attention to the little boiler. I mean, that's not a pump. It's pump's got to be the size of this table. That's what I was used to. So, but it was all relative. So when I started learning radiant floor heating, and it was all trickled down, so to speak. Hey, a pump's a pump, right? It's going to move water around in a circle. So same idea. So that's how I got here.
Very good. Very good. Well, while you're talking, I learned something. WKRP was 15:30 a.m. right there. It says right there on the sheet.
Oh, there you go.
15:30 a.m. There you go.
RTFM, or read the shirt instead.
Read the shirt. RTFS. Right there you go. For me, it was I started out as a child. About the time I could walk, I was going on
Most
jobs
of us
with
did
Dad.
start as childs.
Yes, but I
Yeah.
started in this industry as a child, where Dad used to take me to jobs when I was 5, 6 years old, and fetching wrenches, and he'd have me go out in the truck and mix spotted paint so he could get some work done, and stay out of his hair. So I started out doing stuff like that. I could solder. I was making hockey goals out of scrap pipe when I was like 8, and putting nets on them, and we'd play street hockey, and that started very, very young. And then worked from on and off all through high school. Then I went to college and got the bright idea of becoming a radio guy, and did that for a few years till I reached the end of my talent, which didn't take very long. Took 6 years. 6 years before I ran out of the want to and the can just didn't add up. So went back to working for the family business, and was working with my brother then, and that was not a good idea. And then went to work for Richard Trethewey from This Old House. He had a rep company. So that's when I really started to learn radiant floor heating. I'd installed a bunch, but I really started to learn it there, and then worked for a couple of different manufacturers, reps, before going to Wurzbo in 95 and then Takeo in 07. And that's all she wrote. And
Amen.
Yeah, your first introduction was Stadler.
Stadler, which is the precursor of Vega.
Yep.
Stadler with Jackie Chirac was the very
Yes.
first person I ever spoke to about radiant floor heating, and she taught me most of what I know. Just a wonderful, wonderful person, and just incredibly talented at radiant floor
Agreed.
heating. She
Agreed.
taught me a ton, and to the point where I was calling her up, and I think she was getting annoyed. Said, "What is it now?"
Yeah, the radiant days were fun back then, huh?
Mm-hmm.
Yeah,
Jackie,
we made it up
Bob
as we went
Goodrich,
along.
all those guys taught me a ton. Yeah, it was you didn't know what you didn't know.
Yeah.
All righty then. Well, excellent, guys. Hey, we're out of questions, so we're going to say thanks you. Thanks you. We're going to say thank you. Thank you, and we really appreciate it. And this is the mighty WKRP signing off for another week. And thank you all. Thank you, Randall, Richard, Philip. Really enjoyed having you guys with us again tonight, and it's fun to wrap with you. And really do appreciate it. Thanks for the gift of your time, folks. And we will see you next Wednesday night.
Same bat time, same bat channel.
We're gonna have to
Enjoy,
do
all.
Batman next. That's gonna have to be our
Oh,
name.
we
You know?
have to. We haven't
Yeah,
done it
Batman
yet.
and Robin, you can be Alfred. One of you guys can be Alfred.
Alfred.
So long, everybody. We'll see you later.
See yous.